In this topics packet, we're going to cover the basics of U-substitution. U-substitution is an integration technique that's usually taught right after you learn the power rule and maybe some other rules about the antiderivative of the e to the x exponential function and your antiderivatives of sine and cosine. So I am going to do some problems in this packet that include having to know the antiderivative of e to the x and the antiderivative of sine of x and cosine of x. If you haven't learned those yet, don't worry. There's plenty of examples in this packet that you can look over that you probably have learned at the point of learning U-substitution. So just kind of our main goals here is to understand the concept and the purpose behind U-substitution and learn how to identify when U-substitution is an applicable technique. And then we'll just work through a bunch of examples so we can get better and more refined at this process and technique. So let's just introduce the idea of U-substitution, and let's just read through this as it's important. U-substitution is an integration technique that reverses the chain rule of differentiation. So you can think of this as like the inverse of the chain rule, I guess. Not really an inverse, but reverses is a good rule. We're undoing the chain rule from differentiation. U-substitution is typically used when the integrand, remember the integrand is what's inside this integral sign. So U-substitution is typically used when the integrand contains a composite function and its derivative, or a constant multiple of its derivative. I'll get into more what this sentence means. This is how to choose when to use U-substitution, and we'll get into that as we proceed. Now, something I do want you to keep in mind, U-substitution is just an integration technique. The goal of U-substitution is to take a very complicated problem, do some variable substitutions, typically using the letter U, which is why we call it U-substitution. So the goal is we take a complicated integrand, we do some substitution steps to it, and then we wind up at an easier problem that we can then solve using other integration techniques. So no problem requires, quote unquote, U-substitution. I want to make that clear. If your teacher teaches you that a problem requires U-substitution, they're maybe overstating the case a little bit. No problem requires U-substitution. U-substitution is just a tool to help you go from a problem you don't know how to integrate, let's say, to a problem you do know how to integrate. So it is possible that some very experienced mathematicians can look at this problem here and just know what the antiderivative is without using U-substitution. However, for most learners, we need to go through this process of U-substitution until we are that confident and comfortable. So let's proceed as follows. We are going to explore U-substitution by example. So it takes a few practice problems to get used to what U-substitution is saying and looking for. So again, by example is one of the best ways to do this. The general idea is that I look inside my integrand and I ask myself, do I see a function and its derivative present? For example, do I see a function and its derivative? And the answer to this is yes. The derivative of x to the 6th plus 12 is in fact 6x to the 5th. So because I see a function and its derivative present, my indication is that, oh, I think I can use U-substitution to solve this problem. So what I do is I am going to start my scratch work here. And I'm going to let U equal x to the 6th plus 12. So I'm just going to do a straight substitution. I'm going to pick a new variable U, and I'm going to say that U is equal to x to the 6th plus 12. And at first you're going to say, how did you know to choose that? But through some practice and examples, you're going to get used to choosing the appropriate U. Now, I need to then take the derivative of U with respect to x. So I am going to find du dx. So the derivative of U with respect to x is equal to 6 x to the fifth plus 0, right? The derivative of this plus 12 becomes 0. So cleaning this up a little bit, I get du dx equals 6x to the fifth. Now, one more step here in my Scratchwork structure. What I do is I look at this du dx and I actually am going to separate these differentials. I am going to multiply the dx to the other side of the equation. You'll see why again here in a moment once you get used to this structure. But to start, we pick the appropriate u, we then calculate its derivative, and now I'm going to manipulate the form of its derivative. So multiplying that dx to the other side, I get du equals 6x to the fifth dx. Now, in your Scratchwork, a lot of your teachers are going to skip that intermediary step, and they're just going to identify u and identify du. So that's kind of the main elements we need to proceed with U-substitution. Now, our goal is to look back at the original equation. Do we see how we can substitute out all of the x's in the original integrand and replace them with u's? And sure enough, let's get a little bit bigger of a highlighter just to help us see here. Sure enough, I'm going to see the following. X to the 6 plus 12 is going to be replaced by u. And then if I look a little deeper, I notice 6x to the fifth dx. So 6x to the fifth dx is going to be replaced by du. Let's just say that again and get that written down here. 6x to the fifth. I'm just rewriting the original problem. There it is. Now remember, all of these terms are essentially being multiplied here, so we can rearrange their order. If you prefer to see this in a different order, this is the square root of x to the sixth plus 12 times 6x to the fifth dx written in the back. Again, notice the substitution. The du is equal to 6x to the fifth dx. So this du is going to replace 6x to the fifth dx. And our u, highlighting it in green, is equal to x to the sixth plus 12. That is going to replace what's inside the square root. So the next step is the substitution step. Substitute in u and du. Doing so, based on what I've defined u and du to be, I wind up with the square root of u times du. Right? Be very careful. Pause the video if you need to. All I did was substitute in who my u represented, and then from u, I calculated du, and then I saw there was a match for du as well. I subbed out all of my x players, and I subbed in all of my u players. I'm going to remove some of these marks now so we can continue with the problem. Now, this is the main idea. With my laser pointer, this is the original problem. Looks very complicated to solve, right? Here it is. The original problem is very complicated to solve. Once I substitute in my u and du, that problem is much, much easier to solve. This new problem with u's can be solved using the power rule. So once I've substituted in my u's and du's, I am going to solve using, I'm going to say another method, because there's no telling what method just in general you're going to use, but the whole goal is to go from a complicated problem to a simpler problem, which then you can solve using another method that's familiar to you. As I rewrite, I know that u, the square root of u, can be rewritten as u to the 1/2 du, Normally, we don't write that time sign between the integrand and the du, but it's not wrong to write it. We just normally don't write it. And now integrate using the power rule. This becomes u to the 1/2 plus 1 over 1/2 plus 1 plus c. So if you notice here, I took a complicated integration problem. I did a substitution of variables to get to an easier problem. I did some rewriting to make my life easier, and then I integrated using the power rule. I am not quite done yet, but I'm going to clean this term up because I'm done with the integration part. I integrated. So I integrated, which I added a new page in just to give us more room. This becomes u to the 3/2 over 3/2 plus c, or I could rewrite that 2/3 u to the 3/2 plus c. So one thing I want to say is this is a valid final answer, but there's a but, of course. This is the final answer in terms of u, the variable u. Now, since u was a variable you created, no pun intended there, u is a variable that you picked and you created to make your life easier, we normally don't give the final answer in terms of u. We return the final answer, to x's. So in order to do that, you just have to remember what your u was. Recall, u equaled, I need to scroll back up a minute to find my scratch work. What did u equal? U equaled x to the 6th plus 12. That should be on your page. Sorry for the scrolling. So I'm going to take my final answer from above and then just put the u back. U is equal to x to the 6th plus 12 to the 3/2 plus c. This right here would be considered the appropriate final answer. So let's recap what we did. I'm going to go back through the steps. I looked and follow my laser pointer here. I'm going to move it over to green just to highlight. I looked at the original problem. It was too complicated. I noticed there was a function and its derivative present in the problem. I did some scratch work to pick my appropriate u values, which I then substituted in. I rewrote just to do some housekeeping. And then from here I realized, oh, I can just use a power rule to integrate this. So I integrated in terms of u. I cleaned it up a little bit. And then I put my x's back for my u's. Since u was just a placeholder for what it represented, I returned my u in terms of x's. So the way I kind of explain it to students is u, the variable u, does all the heavy lifting and all the hard work. But at the end of the day, x gets all the glory. So it's like the u team, right? If you think of sports analogy, the u team subs out the x's. The u does all the work to win the game. And then at the end of the day, x gets to stand on the podium and celebrate the final answer. This is the concept of U-substitution, and we're going to continue looking at it just through our remaining examples that vary in difficulty. And of course, there's always little exceptions to U-substitution and tweaks that need to be made, so we're going to look at some of those as we proceed. So let's dive into our next example. Evaluate the integral. Here we have a complicated integral given to us here using U-substitution. Now, I know this tells us what method to use, but let's pretend you were on an exam or something and your teacher did not tell you what method to use and just said to evaluate the integral. You're going to have to get good at recognizing when U-substitution is an appropriate strategy. So the first thing you look for is, do you see a function and some version, which I'll talk more about what that means in a little bit, but do you see a function and its derivative present or some version of its derivative. And yes, I do see a function and its derivative right there. So this tells me when I see that, my first inclination is this problem is a prime problem to use U-substitution on. U-substitution is also more commonly or affectionately referred to as U-sub, just for short. So my U-sub scratch work, since I see a function and its derivative, I'm going to say U is equal to 2x cubed minus 15. Now, I want to be clear about something because this is going to come up in the next example. Our job is to pick the U. We do not get to pick what du is. Our job is to pick U appropriately. Once we pick U, so we look in our problem, we pick U. Once we pick U, we take the derivative of U right here. We don't get to pick the derivative of U from the function. We get to pick U. Then the derivative of U is just naturally whatever the derivative of U with respect to x is. So what is the derivative of this function, this U function with respect to x? It is 6x squared. And then the derivative of that minus 15 is 0. So again, I told you there's that extra cleanup step where then your teacher will probably start automatically moving the dx to the other side. All we did was just multiply that dx over to the other side. So what we have found is we have a u and we have a du here. And the question is, when you look back in your original integrand, when you go back to your original integrand, do you have matchers, I guess I call it. I always think of we're looking for perfect matchers. Do you have a match for U? And do you have a perfect match for du? And if you look here, I know du is awkward, 6x squared dx, but there it is, 6x squared dx. It's okay that it's separated by another term in there. So we did our scratch work. I'm just going to rewrite the original problem. And now I'm going to do the substitution step. So let's do the substitution. Right? The substitution step means all x's are getting replaced by u's. So the substitution step, this term right in here, 2x cubed minus 15 to the 10th. Well, the 2x cubed minus 15 is getting replaced by u to the 10th, right? We need to include that 10th power. And then remember, this 6x squared dx is actually equal to du. So that's getting replaced by du. So everybody got replaced by who it was equal to. Now look at this problem. So again, think about what we've done. We took a very complicated problem. We did an appropriate variable substitution to get to a less complicated problem. I can integrate this problem now using the power rule. This looks like a pretty basic power rule problem. So the antiderivative of u to the 10 is u to the 11 over 11 plus c. All I've done is the power rule. So this is the final answer in terms of u. Right? But this is not normally, since u was a tool we made up to solve the problem, we don't want to give the final answer in terms of u. We need to recall that u was equal to 2x cubed minus 15. I'll scroll down. So remembering that u is equal to 2x cubed minus 15, let's just put that back. Let's put back, right? Instead of having u, let's replace u with who it's equal to in terms of x. So our answer will be 2x cubed minus 15 to the 11 over 11 plus c. So there is our final answer in terms of x. And if you're not convinced yet, remember, take this final answer right here. Take that final answer. Take the derivative of this final answer. Don't forget to use your chain rule. Take the derivative of this final answer using the chain rule. And sure enough, you will wind up with that integrand as your derivative. So let's keep going. More examples with U-substitution. We are going to turn up the heat in difficulty a little bit. Getting on to the next example, 1.3, we're asked to evaluate the integral. So here we have some integral, some crazy looking integrand, and we're told to use U-substitution, but we could pretend that we weren't told what method to use and we were doing this problem ourselves for the first time with no hints on what method to use. The first thing you want to do when you start digesting how do I go about solving this problem is ask yourself, do you see a function and its derivative present? Now remember, before I had said a function and some version of its derivative. What I mean by that is if it's close to the derivative but is just off by a constant multiplier, that's okay. We can manage that. For example, look at x cubed minus 5. The derivative of x cubed minus 5 is 3x squared. Aha, I have an x squared. I don't have a 3x squared, I have a 5x squared, but I have the right structure. Being off by a constant multiplier is okay for U-substitution, and I'm going to teach you how to deal with that. So we have a function and some form of its derivative present. This to me tells me it's a prime suspect for U-substitution, which I'll write U-sub. So here's my U-sub scratch work. So this just takes some wisdom and experience, knowing how to pick your U and then how to proceed. So I pick my U as the function. So once I've picked U, remember when you go about finding du dx, the derivative, you do not get to pick du. Du, or the derivative du dx, is the direct result of what you chose for U. So du dx is the derivative of the function you picked for U. So write down your derivative. Now remember I said we're going to take that extra step of moving that dx to the other side. So some of you are going to eventually stop showing the intermediary step and you're just going to jump straight to this. All right, so I'm just going to put those next to each other. U is equal to x to the third minus 5. Du is going to equal 3x squared dx. Now, here's the issue. Notice in the problem, I have an x squared dx. So I have an x squared dx down in my du, but here I have a 3 and here I have a 5. There's a few ways to go about manipulating this. I teach it a certain way just because my experience has found students make fewest mistakes the way that I've eventually decided on. So since I noticed there's an x squared dx in the problem, in my scratch work, I'm going to divide this 3 over. I'm going to make this a 1/3 du is equal to x squared dx. Get that on the screen. So right now, here's what I have going on. U is equal to x cubed minus 5. 1/3 du is equal to x squared dx. Let's write down that original problem just so we have it. The original problem said 5x squared x cubed minus 5 to the 8 dx. All right, so now that I have everything on the page, let's start that substitution step. So I'm going to say sub in U. This is what we're doing, the substitution step. So remember, you sub in U and du, but not necessarily just du. You need to sub in your du term and your u term appropriately. Let me kill that color. There we go. So now we can see the whole screen. So pay attention here. In blue, I'm going to underline My u is going to replace x cubed minus 5. And then look at what is boxed below. 1/3 du, right here. 1/3 du is going to replace x squared and dx. The 5 there in the integrand is just going to hang out. So let's do that substitution. The 5 hangs out. The x squared dx that I have underlined in pink is going to get replaced by 1/3 du. And then the x cubed minus 5 will get replaced by u to the 8th. So hopefully you've seen where all the substitutions have come from. I'll try to show. X cubed minus 5 got replaced by u. And then the x squared dx part got replaced by that entirety of the 1/3 du. Everybody got substituted out. Now, it's not common form to have du mixed in with the integrand. There's nothing wrong with it. It's just not common form. So normally you're going to see this written as u to the 8th du. Since u is a single term, I don't need parentheses around it. Notice I have a couple constants here. I can combine those. This is 5/3 u to the 8th du. Now remember the whole goal here. I took a very complicated looking problem. I did an appropriate substitution to get everything in terms of a new variable. I cleaned it up. And now I can integrate this down here using the power rule. This is a simple power rule integration. So this will equal 5/3 hangs out. It's a constant multiplier, Then we do the power rule on the u term. U to the 9 over 9 plus c. We can then clean this up. If you want to clean those fractions up, this becomes 5u to the 9th over 27 plus c. That is your final answer in terms of u. But we need to remember that the original problem wasn't given to us in terms of u. We need to put back our our u terms in terms of x's. So go back up and remind yourself. U, so looking up here, u was equal to x to the 3rd minus 5. So now just sub back out. U was equal to x to the 3rd minus 5 to the 9th over 27 plus c. Here is your final answer. So remember, the variable u did all the heavy lifting. It did all the integrating, the cleanup, all the heavy lifting. And then at the end of the day, the x got to substitute back in and get all the glory. All right, our next example here involves an e function, an exponential. So this e is not a variable. That's that Euler's number, that exponential. Doing this problem requires that you know, so I'm just going to make note, this requires that you have learned the antiderivative of e to the x dx is e to the x plus c. So this requires that you have learned this, but most students actually learn this in differential calculus, right? Think about it going backwards. What is the derivative of e to the x plus c? The derivative of e to the x plus c is just e to the x. But you need to have learned this before you can proceed with this problem up above here. So assuming that you've learned that, let's consider, just going to rewrite the original, 4x times e to the 2x squared dx. So this looks like a very, very complicated integration problem. What you need to do is look at it and ask yourself, do you see a function and some version of its derivative present? And I do. 2x squared has a derivative of 4x. It's all right there. So I think we're a prime candidate for U substitution. And I'm going to let my u equal 2x squared. So now I go find my du. The derivative of 2x squared will be 4x dx. Notice now I just bypassed that step of putting the dx under the du. I just immediately moved it to the other side. Now what I have to do is look at my original problem and ask myself, do I have perfect matches to sub in, or do I need to do any manipulation in my scratch work? And I see perfect substitutions. 2x squared will get replaced, and 4x dx will get replaced. So subbing in, I get e to the u du, right? Let's underline it just to highlight one more time. The 2x squared got replaced by u, and then the 4x dx got replaced by du, and I just wrote it in the backfield. So now ask yourself, do you know how to take the antiderivative of e to the u du? And yes, that's one of our rules. The antiderivative of e to the u is e to the u plus c. This is our final answer in terms of u, but now just take your u and substitute what it equals back into place. So really the final answer is e to the 2x squared plus c. So there it is. This is the final answer to the antiderivative of the original problem. Let's keep going. More examples. This one's a little bit more complicated, but does still involve that e function. So again, we look at this problem and we ask ourselves, do I see a function and some version of its derivative present? This one is really tricky to see without prior experience. But I look up here and I see negative 3x squared minus 3x. I do believe I have a version of its derivative down here. You might have to go on some faith for a minute until you see it. But following along, u sub. So if you don't quite see it yet, have a little faith, just take some time, follow along, pause where you need to, and we'll get there. I am going to let u, remember I get to pick u, I'm going to let u equal negative 3x squared minus 3x. So now I am going to take the derivative of u. Remember, I don't get to choose this. I just take the derivative of what I chose. So taking that derivative, negative 6x minus 3 dx. Now, again, pay close attention here. Here, I have a perfect match. So I have a replacement for my u. The problem is, what's going to be my replacement to get rid of the 2x plus 1 and the dx? And I'm going to show you. A little bit of fancy footwork. If I'm clever and recognize, factor out on this right side here, just a little scratch work, factor out a negative 3. If I factor out a negative 3, I leave behind a 2x plus 1 dx. There it is. Oh, my 2's kind of funky. Let's make that better. 2x plus 1 dx. So this negative 3 is extra. I'm going to take it and divide it over to the other side of my scratch work. So this is negative 1/3. I just divided by negative 3. Negative 1/3 du will equal 2x plus 1 dx. There it is. Let's highlight. There's a replacement for u, and then the 2x plus 1 dx is going to be replaced by negative 1/3 du. Let's do that in the substitution step. I'm going to keep it on the page. Substitute. There we go. Sorry, a little spelling trip up. Let's make that replacement. I am going to have e to the u, right? The underlined blue got replaced by u. And then the underlined pink, the 2x plus 1 dx, is going to get replaced by the negative 1/3 du. Notice I put in that multiplication sign because all of these terms are being multiplied. So don't accidentally make it look like you're subtracting or adding. But just if you need to pause and look, the negative 1/3 du replaced the 2x plus 1 dx, and the u replaced what was in the exponent. So just rewriting this down below to give us some more room now that we've made the substitution step. Most people don't like that negative 1/3. Again, it's a constant hanging out in the middle, so let's pull it to the front. We could think of this as negative 1/3 e to the u du, just rearranging. And now this is a constant multiplier rule combined with our e rule. Remember, that constant multiplier of negative 1/3 comes along for the ride, times what is the antiderivative of e to the u? Well, it's just e to the u. So there we have it. We took an antiderivative. We found it. Now it's a matter, though, of replacing what is your u term. Go back up and ask yourself, oh, u was equal to negative 3x squared minus 3x. So back down to our answer. U was equal to negative 3x squared minus 3x plus c. So here it is. This is the final answer. This is the antiderivative of that original problem. Another example. Let's keep going. That's how you get good at these, is by doing enough. Okay, so now we've entered section 2. Section 2 is just applying U-substitution to more complex functions. We're just going to get a little more in depth on U-substitution. This one is especially complicated because it involves a little bit of trickery, I think, with U-substitution. So if I looked at this problem without any prior experience, U-substitution wouldn't necessarily come to my mind. I would want to do some sort of algebra or rearranging or simplification, but just nothing can really be done here. So this takes some wisdom. This takes some wisdom at looking at the denominator and saying, I'm going to do a u substitution for that denominator. I'm going to let u equal x plus 6. Again, this just takes wisdom and experience. Therefore, my du is going to equal, again, you don't get to pick that, take the derivative of x plus 6, which is 1, and then it gets a dx since you took the derivative with respect to x. So my u is equal to x plus 6. So here it is, let's underline it. X plus 6 is going to get replaced by u. My du is just equal to 1 dx, or in other words, dx. So my du is going to replace dx. I have a problem. The problem is, what about this 5x? Who is going to replace that 5x? Right? The goal is to get all u's into place and remove all x's. So here's the fancy footwork. This is a little sneaky until you've done it. In my scratch work, I know that u is equal to x plus 6. Therefore, I know that u minus 6 is equal to x. This x up here is going to get replaced by u minus 6. So again, we're going to go make our replacements. X is going to get replaced by u minus 6. X plus 6 is going to get replaced by u, and then dx is going to get replaced by du. Let me take off those boxes. We're subbing out every single x player for u players, right? So just rewrite the original 5x over. So this will equal, in terms of u, I'll just make a note on top, in terms in terms of u, when we transfer everything to u's, the 5 will stay on top. The x on top will get replaced by u minus 6. And then the denominator, the x plus 6 in the denominator, will get replaced by u. And the dx will get replaced by du. So there it is. We had our original problem. We did a very clever and wise, this takes a lot of experience to know to do this u substitution. Now the hope. The hope is that we went from a bad problem, here's my sad face. The hope is that we went from a bad problem to a happy problem. Did we in fact do that? At first look, you might think no. At first look, you might think, hey, wait a minute. This u problem is a similar kind of mess, but I hope to convince you otherwise. Let's clean up the u problem. Distribute the 5 through. This becomes 5u minus 30 over u du. Now, keep going with some algebraic simplification. Split your fractions. Clean up. This becomes 5 minus. Now, I'm going to write this a little differently just for emphasis here. There's no reason you have to pull that 30 out in front, but I did. So there we have it. We've cleaned it up. And now you're just integrating. In terms of u, integrate 5. So let's do that. We actually know that. This is 5u minus 30 times, what's the antiderivative of 1 over u? That's one of our special rules, right? The antiderivative of 1 over u is ln of u, specifically ln of the absolute values of u, plus c. So there you have it. We're not done. We need to put this answer back in terms of x, but just to highlight what we did, let's go back to it. We took a complicated problem. We did an appropriate variable substitution to rewrite it. We did some housekeeping to clean it up. We cleaned up. Then we integrated. We did the integration. So u, the letter u, did all the heavy lifting, and we did the integration. And now it's just a matter of giving x all the glory. So go back up. See, you have some u's here. You need to replace those u's with what they equaled. We have to recall that u is equal to x plus 6. So x plus 6 is going to replace every one of our u's. So our final answer becomes 5u, but u gets replaced by x plus 6 minus 30 natural log of x plus 6, absolute valued, plus c. There it is. This is the final answer to the original problem. That is the antiderivative of that original integrand. That's a tough one. This up here, this fancy footwork, I consider it, knowing to make this little adjustment in your scratch work just takes experience. Let's just do more examples. Our next example, 2.2, deals with an exponential function and looks a little bit more straightforward. Again, we're told to use U-substitution, but let's say you weren't told that. How would you know to use U-substitution? Again, just a little wisdom and experience. Do you see a function and some version of its derivative? I would argue I do. 5x is my function. The derivative of 5x is 5, and that's just a constant which I can manipulate. So watch how we tackle this problem. We're going to do U-substitution. The wisdom that I have, which you're going to get soon with enough experience, you have to do enough of these to have the experience and wisdom to pick U properly. And again, it takes failing and failing and failing and picking the wrong U until you start to see the light and get this wisdom. So don't get frustrated as you're going through these problems. It's okay to pick wrong, make adjustments, and go back to the drawing board. So my wisdom tells me let my U equal 5x. Now, take the derivative of u with respect to x, which is 5 dx, and then Looking back in the original problem, I only have a 5x and a dx. So I have a 5x right here, and I have a dx. So this 5 is problematic. I don't want that 5 in the mix. That's when I divide it over. So I'm going to manipulate the constant by dividing it over. 1/5 du will equal dx. So there we have it. There is the perfect match for dx. So now when I do my substitution step, sub in my u's, this is going to be the integral of e to the u times 1/5 du, right? This entire dx got replaced with 1/5 du. Now, most people tend to get comfortable with pulling the constant to the front. And then we integrate from here, right? Now we're in an easier problem to integrate. I know the antiderivative of 1/5 e to the u. It is 1/5 e to the u plus c. And then don't forget, you need to put back your u. Your u needs to get replaced by what u equaled. U was equal to 5x. So put it back, and there it is. There is your final answer to the antiderivative of the original problem. More examples, right? That's what we do to get better. Practice, wisdom, experience, that's how you get good at picking u. So let's get a trig function in there. Again, this example assumes you learned. So this assumes you have learned that the antiderivative of cosine of x dx is equal to sine of x plus c. So again, this is kind of a fact that can come from thinking in terms of taking the derivative of sine x or take the antiderivative of cosine of x. So you will have had to learned this fact to perform this u substitution. So assuming you've learned that, let's take this integral down. And we have to look at this and say, okay, I believe this is a u substitution. A little wisdom and experience tells me let's pick my u to be this inside function here. And watch what happens. U is equal to negative 6x. The derivative du, well, what's the derivative of negative 6x? It's negative 6 dx, right? We move that differential dx over. Now ask yourself, there's a perfect match for my u. I need to also substitute out dx. So this negative 1/6 needs to move out of the way, clear out. Divide it over. We've done this a few times now. So divide over by negative 6 becomes negative 1/6 du is equal to dx. And now we have a perfect match to replace dx with, right? We're looking for perfect matches. So substitution step, sub in u's. So sub in our u's. I'm going to put just a little dividing line to separate our scratch work. Sub everyone in place. This becomes the antiderivative of cosine of u times negative 1/6 du, right? The u went in for the negative 6x and the negative 1/6 du went in for the dx. Again, most people prefer to pull the constant of negative 1/6 out to the front. But it's just a constant multiplier. Again, some people even prefer to pull it all the way out to the front. Says the same thing, no big deal to me. We know constant multipliers come along for the ride. Then integrate cosine of u du. Well, the antiderivative of cosine of u du is, well, the negative 1/6 comes with us, times the antiderivative of cosine of u is sine of u plus c. So there it is. There is the antiderivative in terms of u, but now we need to put x back in. U was equal to negative 6x, so here it is. This would be our final answer. There's another U substitution example. Again, if you need to pause these videos, rework these problems, rewind, listen again to what I've said, write it down, take notes until you start feeling like you have some wisdom to appropriately pick U in context. Let's keep going. A little bit more. Oh, this one looks awfully scary. A trig function with a logarithm in it. So this requires knowing. Well, this requires that you know. Yep, this assumes you know or have learned that the antiderivative of sine of x dx is equal to negative cosine x plus c. So you will have had to have learned this fact, the antiderivative of sine of x, to proceed with this problem. So I'm going to separate that and let's bring this problem down. This looks awfully intimidating to me. It's the sine of the natural log of x over x dx. And if we're going to use U substitution, remember your guiding light is to ask yourself, do you see a function u and its derivative present? Well, it depends on how your brain works. What if I rewrite this problem? Let's say I put a 1 multiplier over here. You can always have a 1 multiplier. Let's say I rewrote this problem the following way. I didn't do anything. I haven't changed anybody. All I've done is restructured the problem. Now, do you see a function and its derivative present? I definitely do. Let's continue then. Our U sub scratch work. I'm going to let U equal natural log of x. Because when I take the derivative, du, what is the derivative of the natural log of x? It is 1 over x dx. And there it is. I have perfect matches. Look, I have an ln of x right there. And then I have a 1 over x dx, a 1 over x dx right there. I can substitute everybody in to my substitution step. So my substitution step will look like the sine of u, right? The u replaced the natural log of x. And then 1 over x dx, I didn't require any fancy footwork or moving around in my scratch work. 1 over x dx is just straight up equal to du. So there it is. This is the substitution step. Now, did I take a very, very complicated looking problem and transform it into an easier problem? And I would say yes, because I know how to integrate sine of u du. The antiderivative of sine of u du is negative cosine of u plus c. But remember, the x gets to go back in. So really it's negative cosine of ln of x plus c. There it is. This is the final answer to the original problem. Let's keep going. We got a few more examples to look at. So this 2.5 example, exactly what it says, increasing in difficulty with some trigonometric functions. Evaluate the integral using U substitution. This is a great problem because we're looking for, if we're going to use U sub, we're looking for some function and some version of its derivative present. Well, some people will say, hey, well, the derivative of sine is some version of cosine. So there it is. But what if somebody else says, Well, wait a minute. The derivative of cosine is some version of sine. That's true as well. How do you know which to pick? Do we pick u equal to cosine of 2x or u equal to sine of 2x? This is a great question. How do we know which one to pick? Since their derivatives are versions of each other, this becomes complicated. So one of the guiding principles on how to pick is you can never have du bothered. That's the way I think about it. Du cannot end up in a denominator. Du cannot end up in a square root. Du cannot end up in an exponent. Du has to end up unencumbered. So what that means, so let's say I pick the left side. Let's say I'm going with u is equal to cosine of 2x. So I do my process. I take du, which is the derivative. Derivative of cosine of 2x is negative sine 2x times 2, that's the chain rule, dx. Now, if I'm looking for perfect matchers in my original problem, I see that I only have sine of 2x. So cleanup is required here. First, I'm just doing a little cleanup. Then I'm going to divide over the negative 2. So this is negative 1/2 du equals sine of 2x dx. All right, so I've done some cleanup. Now watch. What I'm going to do is I'm going to substitute in, right? Let's do a substitute in. U is going to go in for cosine of 2x. And then, look what's going on. I have a sine of 2x as an exponent, and then dx is down below. This is problematic. I don't have a sine of 2x times dx. This is bad. So, big frowny face here. I don't have a sine of 2x dx. I have a sine of 2x as an exponent, and then I have a dx on the ground. This term does not actually exist in our problem. This is the wrong choice. You have to go through a few of those mistakes, though, to realize you have the wrong choice. Again, wisdom and experience only comes from wisdom and experience. I know that sounds stupid, but you have to go through this process. You've got to make this mistake to realize that's the wrong path. The correct path will be picking u to be sine of 2x. Because watch what happens. The derivative du of sine of 2x is cosine 2x times 2, chain rule, dx. Because I look in the original problem and I don't see a 2 anywhere, I'm going to divide it over to the other side in my scratch work. So really what I have is 1/2 du is equal to cosine 2x dx. And look, I have perfect matches. Go back to the original. U is going to equal sine of 2x up here in the exponent. Down on the ground, we've got cosine 2x dx. We've got cosine 2x dx. That's going to get replaced with 1/2 du. Let's do that replacement step down below. So I'm going to rewrite the original just so we can see it. The original was cosine 2x e to the sine 2x dx. Now, I am going to take my u. U is going to replace the sine 2x. So let's go to the next line. This is going to become e to the u times, and then remember the cosine 2x dx. I guess I should do it in my pink to be consistent. The cosine 2x dx gets replaced by the 1/2 du. Once again, most people like to pull that 1/2 to the front, or they pull it all the way out. And then you say, hey, wait a minute. Look at this. I took a very complicated problem. I did a substitution and I got myself to a much easier place. I know how to integrate 1/2 e to the u. It is 1/2 e to the u plus c. And then remember, put your choice of u back. What did we choose for u? You might have to scroll up and find, but I remember off the top of my head, our u choice was sine of 2x. So here it is. There is our final answer at the end of the day. I think we've got one more example in our packet to go through. We'll go through that and we'll consider this good as far as learning the basics of U-substitution, though I'll say we went fairly far beyond the basics here. We got in pretty nitty-gritty with some tough examples. So let's look at one more advanced U-substitution. Remember, you're looking for a function and some version of its derivative. Well, the derivative of some x squared is 2x. Well, look, there's an x. So don't worry about the constants again. I just think the derivative of x squared is some form of x. So I have x squared and some form of x. This is a great choice for u sub. Now you'll get used to, in U-substitution, you want to be as greedy as possible. And what I mean by that, if there's a constant hanging out with your main function, take the constant with you in terms of who your u is. So don't just pick u to equal x squared. Be greedy with the constant 1 minus x squared. Because when you take the derivative, what happens to that 1? The derivative of 1 is 0. So it doesn't end up bothering us in terms of du. So be a little bit greedy with u, take the constant. Now when we go to calculate du, it's negative 2x dx. Then we look up at our problem. The 1 minus x squared in the square root is going to get replaced by u. And then, oh, wait a minute, I have an x dx. I only have an x dx, so ignore the 3. Move the negative 2 over in your scratch work. So we have negative 1/2 du equals x dx. And there it is. There is that perfect match, x dx, for what we have going on up there in that equation. If this helps, I'm going to rewrite this problem and then show it in a little bit different light. Some of us don't quite see it yet, so it's important to think about this rewritten. Before I do my substitution step, remember, I can rewrite this problem as 3 over 1 minus x squared times x dx, right? This x that was in the numerator can just be written on the side as multiplication. That says the same thing. And maybe this makes it a little bit easier for you to see your x dx and who it's going to get replaced by. So sometimes just rewriting the forms can make life easier. Let's do our substitution step. So sub step, I'm just going to abbreviate. This is our substitution step. So substitute in all your u's. This is going to become 3 over the square root of u times negative 1/2 dx. That's who everyone got replaced by. Now we got a mess of constants, so let's clean up carefully. I'm going to pull the 3 and the negative 1/2 out in front of the entire integral. Multiplying those together gives me negative 3/2. And then don't forget there's a placeholder of 1 over the square root of u du. There it is. Sorry, I wasn't on the page. So all I've done was I pulled those circled constants out to the front. Let's just highlight that one more time. I pulled the constants out to the front. I left behind the placeholder because my square root of u is still in the denominator. Now ask yourself, do you know how to integrate this function? Well, I think I do if I do a little fancy footwork. Let's do a little bit of cleanup. This term, the current integrand, can be rewritten as u to the negative 1/2, right? The square root gets rewritten as a 1/2, and then to pull it out of the denominator, it becomes negative. And now look, this is just a power rule. So the negative 3/2 comes with us, and we do the power rule, add 1, divide by the new power on the u term, and add a plus c. So all I did was, right, my constant came with me, and then I did the power rule on u to the negative 1/2. I'm going to clean this up just so we have it. Clean it up. This was negative 3/2 times u to the 1/2 divided by 1/2 plus c. Just for practice, I'm going to keep cleaning. This is negative 3/2 times. Now dividing by 1/2 is the same as multiplying by 2. And then one more step, I can reduce my fraction. So at the end of the day, I end up with negative 3 u to the 1/2 plus c. This would be my final answer in terms of u. Let's write that. Final answer in terms of u. But remember, we don't want to give our final answer in terms of u. X gets all the glory. So we need to go back up to our scratch work. Important to have scratch work. Remember that u was equal to 1 minus x squared. So our final answer should be negative 3, 1 minus x squared to the 1/2 plus c. And remember, this was the antiderivative to the original problem. And the original problem was 3x on top over the square root of 1 minus x squared dx. There it is. So here's what we found at the end of the day. And once again, if you're unconvinced, right? If you're unconvinced that this is our big f of x and this is our integrand, our little f of x, take the derivative of your final answer. Don't forget to use your chain rule, all the rules required. Take the derivative of this final answer, and you should get that integrand. This wraps up our U-substitution. This is a lot of examples involving trig functions, polynomial functions, power functions, square roots, exponential functions. You've done a lot here. You're going to do a lot more in your own class, but hopefully this is enough to get you going with U-substitution.